So now let's get into more details. We're going to be looking at the science and the technology side of things. Cedric talked about this. Others talked about it as well. Artificial intelligence, of course, is not in any way reduced merely to a scientific or technical issue. However, it was interesting for us to look at the sort of progress that's been made. We've talked about neurons and learning, and so we have a session. We have a session here between three people. In fact, we have Stéphane Mallat, who is at home here because he has the chair for mathematics and artificial intelligence here at the Collège de France. I don't think I have to introduce him. Stuart Russel is a professor at Berkeley. He's also on many different institutes such as Future of Life, which looks at existential issues. And everybody who has studied artificial intelligence would know about Stuart because he has written the book that everybody has read on the subject. And Joshua Benjo, who is a professor at Montreal, he's the head of the Montreal Institute for Learning. MILA, I think it stands for. I'm not sure what it stands for. He couldn't be with us physically, but he sent us a video. So we'll start with the video.
This is Joshua Benjo from Montreal with a few words about the state of research in AI and deep learning. As many of you know, AI has made surprising progress over the last few years. However, we are still far from human-level intelligence, both in terms of the level of abstraction that computers are able to master and in the generality of this intelligence. Humans are able to understand many different aspects of the world, whereas current state-of-the-art systems are very, very specialized. To approach that level of generality, some of us are investigating a very exciting hypothesis that there may be a few principles, like the laws of physics, a few principles which could explain our intelligence, the intelligence of animals, and could help us build intelligent machines. We already know a few of these principles. For example, with convolutional nets, which are deep networks for computer vision, we exploit a form of hypothesis about stationarity in time and space. In other words, as you move in time or you move in space, the same laws apply. Another example is what we call compositionality. In other words, complicated and interesting functions that we need to learn are obtained by building together multiple pieces corresponding to different neurons, different layers, and this is what gives rise to the depth in deep learning. Now, the old neural nets from the 90s were successful at pattern recognition, like recognizing handwritten digits, but we've made progress in many different directions since then. And in particular, the new networks can handle much more general data structures, such as sequences, tree-structured data, graph-structured data, like what you have in the structure of the web or in the structure of molecules. In my group a few years ago, we came up with advances in what's called attention mechanisms, which have given rise to pretty impressive progress in machine translation, the ability to translate from one language to another. And everybody can use these advances when they go to Google Translate, for example. These attention mechanisms make it possible to use neural networks for all kinds of data structures, but also to read from memory, to write from memory, and to learn to do that in a way that will be useful for a task of interest. Now, in spite of all this progress, there are still pretty striking limitations to current neural networks. If we look at the kinds of mistakes they make, they highlight the limited understanding of the world that those machines have, and in particular, a limited understanding of its causal structure. So in my group, we're betting on two directions of research which are intertwined to try to move beyond those limitations. So the old idea that really motivated deep learning that we're continuing to push forward is that our networks must be able to learn by themselves high-level abstractions and disentangle, separate, recognize the underlying explanatory factors. And as we are doing this, we're actually linking old ideas from classical symbolic AI and reasoning with modern deep learning. One thing that is related to this is how the learner will discover that information about those causes, those explanatory factors. And we think that acting in the world, acting in the environment is a key ingredient for this, so that the learner can explore the world to find out the causal relationships, relate actions and representations, and be able to model the world and predict how it will evolve in the future at a high level of abstraction, so that it can plan in it. And this will combine deep learning, reinforcement learning, and unsupervised learning. To close, I would like to reiterate the importance of discussing the social impacts of AI. These techniques are already powerful and will become even more so, so they could be misused by a few and lead to several dystopic futures. Or we could think and act collectively and wisely to put AI to the service of the common good. It's our choice.
Alors, on voit bien que même quand on parle des fondements...
So when we talk about these basics, when we're talking about those who have actually invented artificial intelligence, you can see that all these same questions occur. And now, earlier on, Justine Cassel and Laurine Stadwitz had 10 minutes to talk about the subject, and I'm going to give you 3 minutes to talk to us about machine learning and neurons. Well, let me start off by trying to demystify the very strange idea of artificial intelligence. Of course, there are many techniques that have been developed, but in the last 10 years, artificial intelligence has become huge because of computer learning. How does computer learning actually work? Well, the aim is to be able to answer a question which has been raised based on data. For example, identify an animal in a group of images or diagnose something based on biomedical data that is provided. So how does it operate? The idea is that you have an algorithm. You have a sequence of instructions that has one specificity, and that is that it includes many different parameters that are not fixed in advance. These parameters are fixed during the learning process. Examples are provided to the algorithm, and the algorithm will try to fully understand the data without making mistakes. For example, if there's an image of a cat, make sure that he says it's a cat and not a dog. And the aim is obviously to be able to generalize. The algorithm, therefore, should be able to find the right answer for the data which has never been seen before by the algorithm. The point of it is that the algorithm finds a form of regularity within the data, and it allows it, therefore, to extrapolate and find the reply or the answer. Now, if you have to measure your child's height every year and then draw a curve which allows you to extrapolate and understand how tall your child is going to be. Now, drawing that curve is easy, but where it becomes more complicated is that these algorithms are based on many different variants. If you look at an image where there are 1 million pixels, it's going to be important to find regularity in all those variables, and that is what research is looking at, so that new algorithms can be developed. Many new ones have been developed, and Joshua Benjo talked about this. Networks, neuron networks. These are in layers, and they are in fact connected through each other. In fact, in the 90s, there were some particularly deep structures that were developed. And what was interesting, this was developed by Jan LeCun, and what was interesting is that these neurons could actually clearly understand these issues. And the main mystery is, why do they generalize? Stuart?
So the kind of learning that Stéphane has described, and I apologize for speaking in English, you'd probably be grateful that I'm doing that and not French. So the kind of learning that Stéphane has described is called supervised learning. Joshua also mentioned something called reinforcement learning, and this is very common in the real world when humans are learning to do things. So for example, if I'm learning to play chess, no one is telling me at every move, okay, this is the correct move to make, this is the correct move to make. That was the wrong move to make, right? I play chess against Kasparov and I lose, and that's what we call a negative reward for me. And it's a very small positive reward for Kasparov, and so perhaps he learned something too. If I keep doing that, if I keep getting the negative rewards and positive rewards from success and failure in some complex task, eventually I can learn to perform that complex task well. So this might be riding a bicycle or speaking French or any number of other tasks. We actually receive very little in the way of feedback signals in training. We actually just have to operate mostly in the real world as it comes. So, you know, when you go to a new country and you go to a restaurant and you see a new kind of food, you learn that concept, and then maybe someone at some point tells you what it's called. But you're learning that concept with no direct feedback from a supervisor teaching you that this is an example and this is not an example. It's just part of living that we gradually accumulate a conceptual understanding of our environments from our raw perceptual information. So this is sometimes called unsupervised learning, and just simple mathematical analysis of how much data we get from the world tells us that almost all the learning that humans do is some combination of reinforcement learning and unsupervised learning. And we have, as yet, not a very sophisticated understanding of unsupervised learning.
Alors justement, quelles ont été les avancées les plus récentes?
So what are the most recent breakthroughs? We know that there's been a lot going on. Some years ago there was deep learning, which really shook things up. There was Alpha Zero. There were many different thresholds, and there was the Go game issue. Anything new, Stuart? Would you like to start?
So one point I'd like to make about these breakthroughs that you described is that from the inside of the lab, it looks very different. All of these techniques have been developed over decades. For example, the method that AlphaGo uses to play Go, to learn to play Go successfully, was first exhibited in the late 1950s by Arthur Samuel with a program that learned to play the game of checkers. And then gradual improvements were made to those algorithms and representations until at some point we cross a threshold which makes it into the public consciousness. This happened with chess when Kasparov lost to Deep Blue, but that was not a breakthrough. That was simply a continuous process of improvement that took place over decades, and it just happened in 1997 to cross a threshold where it became slightly better than the best human being. But there were no research breakthroughs involved in the Deep Blue system itself. And this is a very common phenomenon. So what we're seeing now with applications of deep learning is the result of decades of continuous basic research in the lab crossing various thresholds. One threshold is in speech recognition, where it's now very useful. It used to be terrible, particularly if you had an English accent, because all the systems were trained with American accents. For me, it was mostly unusable for a long time. I'm sure French people have the same issue. But now, all of our cell phones have actually highly competent speech recognition. Machine translation, again, has gone from being very much a research prototype to a tool that I use. I have to pay French taxes, like most of you. And so I use machine translation to translate the completely unintelligible French on the tax forms into completely unintelligible English. So it doesn't really help me very much, but the translation itself is very good. And then, because of advances in computer vision, many of which are based on deep learning, we also see capabilities like self-driving cars. And again, the first self-driving car was in 1988 in Germany, and we have gradually improved the technology through the application of machine learning and other techniques to the point now where some of the self-driving car companies are doing extremely well, and they're approaching the level of performance and safety that would make it possible for ordinary people to use these cars.
Stéphane.
Peut-être je vais apporter un...
Well, perhaps I might shed a different light on the subject. I don't really think it's business as usual, as Stuart seems to think. I think there was a fundamental issue that took place, which was the quick acceleration of speed and also mass collection of data. That meant that we went through a certain threshold, and therefore the algorithms are performing better. Much better than expected. Nobody, in fact, in our group thought that in 5 years' time there would be face recognition algorithms that were actually better than human at recognizing faces. Nobody thought that self-driving cars would be moving around in our cities. So this went that fast because of research, obviously, but also because of this capacity to process mass data. And because of that, we can say it's gone beyond artificial intelligence itself. It's also gone to applications, area of physics. Our minister talked about it earlier on, but also has an effect in the area of sociology. There's a whole gamut of applications which is much greater. And therefore, research today is not looking at just single applications, but covering many different sectors.
Alors, peut-être on peut se poser la question maintenant.
So perhaps we can ask another question. What do we have to do now? What next? Our systems, our intelligence systems don't have the common sense level of a cat or a spider, maybe, so that'll keep Cedric happy. But where are we going to go now? We're not trying to forecast the future, but how do you see things? What are the present stakes in the area of science and research? I'd like to go back to what Stuart said, and this concerns the bias. Speech recognition, for example, working on, for example, American accents, or did for a long time. They may not necessarily pick up other accents without even talking about other languages. So does this mean obviously just getting more data? Does it just mean accumulate data? Is that all that we need? And then supervised learning doesn't work that way. Well, I think this question of the bias, of course, is very important. But also what is important is to open the black box. And that's what Cedric talks about in his report. And by opening the black box, there are two major issues, and they're slightly different. The first issue is to try and understand why the algorithms are going to be so efficient in generalizing the information, and when are they likely to make mistakes. And that, of course, is indispensable when you're dealing with health issues, the medical field, or self-driving cars, automated cars. And also, we are in a development and experimental phase. Maths is slightly behind, and therefore it's a bit difficult not only to manage the algorithms. We understand the programs perfectly, but the specificity of the answers from the algorithms. And this is because there are many different variables. And here, what is important is trying to understand the geometry, the statistics of the variables. And these are difficult issues because these are the same sort of questions that you may have to find in fluid dynamics to understand materials science. So there's a lot of fundamental research which is going on, but it's also very important because that is how we can prove that the system is going to be reliable. And also we can also make sure that the bias doesn't somehow distort the data. But the other point concerning the opening of the black box is because we have to be able to explain why. Why will an algorithm get a certain data or a reply? It's very important because this allows us to structure knowledge, and we can operate with many more examples. If, for example, you have to meet or come across a lion 1,000 times in the savannah so that you know it's a lion, you're unlikely to survive to tell the tale. So you've got to be able to understand these things more quickly, or at least the causal connections more quickly. Now, when you have very complex issues, this question of causality becomes a little weaker. If I tell you that in 1 week's time it's going to be sunny in Paris and somebody says why, well, there's no simple answer. There are thousands of reasons why and bits of data. And if you actually try to bring it down to one single fact, you're going to be telling a story which has nothing to do with the truth. And this is the same in philosophy or sociology or any other discipline. The fact that you have to find a cause and an explanation is something which is extremely difficult. It's practically impossible. And therefore, there's a whole range of areas that we have to look at more closely, find the issues of causal. For example, I have a match, I strike a match near my skin. The chances I'm going to get burnt. But you can have the same sort of thing in medicine, in the law, in other sectors. We've got to understand, but we can't always explain why. So knowing how to respond to potential mistakes that a machine may make is very important. And as Francois said quite clearly, data could, in fact, completely distort the machine's response. So the machine is not always 100% reliable. Stuart probably might have a different point of view.
So I think I want to re-emphasize something that Joshua said, that we are far from achieving human-level intelligence with these kinds of deep learning systems. And one symptom of that is the kind of mistakes that they can make. And Google has been doing a good job of actually illustrating their own failures. There's a nice photograph of essentially a street sign, which I think says something like no parking. And the learning algorithm describes it as a refrigerator full of food and drink. So when you see that, you realize actually, even though there are some impressive examples of recognition, probably it's not really understanding the image at all in the way that a human understands the image. And this comes back to the question of explanation. We actually don't know really what the networks are doing at all, and we don't know why they're as good as they are in their accuracy. But one obvious thing about deep learning systems and neural networks is that they are circuits. And they lack the expressive power that we have, for example, in the English language or the French language, or even in programming languages. So some hypotheses that can be expressed, in one page of English or one page of a programming language require 1 million pages to express in a circuit. And that means that circuit-based learning systems cannot learn those concepts from any reasonable number of examples. And we may actually be seeing some of the limits of what you can do with these circuit-based learning techniques, that for some tasks, yes, we can get by with only 1 million examples, but for other tasks we may need 1 billion examples, and for other tasks we may need a trillion examples, and the universe just isn't big enough to provide that many examples for learning some more complex concepts. So that's one of the big steps that has to be made, is to move from circuit languages to much more expressive kinds of languages which inherit some of the formal properties of mathematical logic and programming languages, but still retain the flexibility and the learning capacities of deep learning systems. Another capability that seems to be missing from current learning systems is the ability to know things. Now, humans obviously know things, and we reason with that knowledge to figure out new things. This is just fundamental to what we think of as intelligence. But at the moment, we cannot describe deep learning systems as knowing anything. They do not exhibit the properties of compositional knowledge and inference or reasoning from that knowledge to derive new information. And it's not to say it's impossible to solve that problem, but this is at the edge of what we understand how to do.
Et ça, c'est un problème mathématique.
And that's a mathematical problem. It means that we don't actually understand all the structures that exist way beyond all these algorithms and masses of data. And that really is a question. What is the knowledge that these networks acquire? That's a real issue. Thank you. Thank you. I think everybody will agree that this was really clear, and thank you very much.